Hello, guys, and welcome to Aerominds Training Center. So now we are starting with the chapter 2 atmosphere, and the part is fourth part. So in the previous videos, we have completed the basics of intro of the atmosphere, the density part, the dynamic pressure, everything. And now we are going to start with the airspeed. Okay, and the very first thing uh, I want you to forget is the idea that airspeed is simply how fast the aircraft is moving, like the speed of the car on the road. The idea is wrong. Okay, so I want you to forget that. And in aviation, the speed is not just measured like the road speed. Okay, airspeed is not just measured directly at all. And this is the foundation of the entire topic which we are going to study. And I hope you guys understand one very idea clearly, that everything else will automatically start to make sense. Okay, so an aircraft does not have a speed meter, as we know, speedometer. As an aircraft has a, as a car, it does not have a speedometer. So a car has a speedometer in which we can see how much the pedal we press, the speed will increase. But in an aircraft, that is not the case. Okay, so the aircraft has a airspeed indicator, which we call ASI. Okay, and the airspeed indicator is not a speed measuring device. Okay, it is actually a pressure measuring device. Remember this: speed measuring, no, it is a pressure measuring device. Remember this: pressure measuring device. Okay. Now it is basically so when you look at the needle of the SI, okay, that needle is not reacting to the speed. There's a needle in the ASI. Suppose this is the ASI. There's a needle here, and it has written 10, 20, 30, 40, 50, 60, 70. So the needle is not showing the speed of the aircraft. Okay, it is, the needle is actually reacting to the pressure changes. Now, what pressure are we talking about? Okay, so we are talking about the dynamic pressure here. It responds to the dynamic pressure. Remember, it is the dynamic pressure. Okay, and dynamic pressure is basically the pressure, as I've told you, which is created because of the aircraft is moving through the air. Okay, and when the air is hitting the pitot tube, that moving air create some pressure, and that pressure is what we call, is what the instrument is sensing. Okay, the dynamic pressure. Got it? Now here comes the formula for dynamic pressure. And even if you don't like the formulas, I want you to understand this very basic formula, what it is trying to say. Okay, so dynamic pressure is equal to half rho v square. Okay, now rho means the air density and v means the true airspeed. Okay, rho is the air density, v is the true airspeed. Okay, so the formula is 1 by 2 rho v squared. Now, what does this tell us in simple language, if you ask? So it tells us that the pressure which is felt by the aircraft depends on two things. It depends on just two things. Now, these two things is, the first is how dense the air is, the dense the air is, how dense it is, and the second is how fast the aircraft is actually moving through that air. How fast the aircraft is moving through that air. Okay, so if the air is dense, even a low airspeed can create high pressure. Got it? And if the air is thin, you need more high speed, more higher speed to create that same pressure. Now this is extremely important for you, because the airspeed indicator uh, only feels the pressure. Okay, it does not know the speed, it does not know the altitude, and it also surely does not know the temperature. It only knows the pressure, so it responds only to the pressure changes. Okay, now this is why we clearly say that it is a pressure altitude, it is a pressure system and not a speed system, speedometer. It is not a speedometer. Okay, now here comes the exam important line. The airspeed indicator does not measure the speed directly. Okay, it measures the pressure and then converts that pressure into a speed indication. Got it? So remember this. We'll now mark. Now the airspeed, this section reinforces the fundamental idea that airspeed is not direct speed measurement, it is a pressure based indication. Got it? Now comes the airspeed indicator's basic principle. The ASI is essentially a pressure gauge, and the needle responds to the dynamic pressure, and the dynamic pressure is given by q is equal to half rho v square, where rho is the density and v is the true airspeed. An important note is the ASI uh, does not measure the speed directly. It measures the pressure and converts it into speed indication. Okay. Now, basically, the next thing is the next question you might have is how does it convert the pressure into the speed? Okay. Now, this is where the calibration comes into the picture. Okay. Now the airspeed indicator is calibrated at the sea level density. Okay, sea level conditions, or you can say. Okay, that means when when the manufacturer makes this instrument, they assume that the aircraft is flying at sea level. Okay, the manufacturing, suppose Cessna, they are the not the Cessna, basically the one who are making the airspeed indicator. So they are thinking that the aircraft is flying at the sea level with the standard temperature, with the standard pressure, and with the standard density. Okay. Now the standard density, the sea level density, has a fixed value, and that value is 1.225 kilograms per meter cube. Okay. You do not need to memorize the unit complete deeply, but you must remember that the number for the exam, 1.225. Okay, this is the IAC sea level density. So the ASI is actually built in such a way that if the air density is 1.225 and the pressure sensed is corresponding to a certain value, then the needle will show a particular speed. Okay, and this calibration works perfect only at the ISA sea level. Remember this, ISA sea level. Got it? Now, if you think logically, do we always fly at at the sea level? No. Okay. Do we always fly at this or at the standard temperature? That too also no. And when you climb to an altitude, your air density will decrease. The density will decrease, and so the instrument is still assuming that you are having the sea level density, but the real density around that aircraft will be different. Okay. Now, because of this, the speed which is shown on the SI is not the actual speed of the aircraft through the air. Okay, this is very important conclusion. The ASI is honest; it is doing exactly what it is designed to do, but the assumption it is based on is no longer in the real flight. No longer true. It is no longer true. Got it? So remember this: the ASI is calibrated assuming sea level density. The standard density is 1.225 kilogram per meter cube, and because of this, the airspeed which is shown on the SI will be accurate only at the ISS sea level. And in real flight, which means higher altitude and different temperature, the density will change, and therefore the indicated speed is not the actual speed of the aircraft through the air. It will be different. I hope you guys get it. Now we'll talk about the now we'll understand the types of airspeed. Okay, types of airspeed explained, because DGCL loves to test whether you understand the difference between what the aircraft is actually doing and what the instrument is showing. Okay, and also for your own learning, you need to know that. So first, let us talk about the true airspeed. Uh, True airspeed is TAS, or it is also known as TAS. It is actually the actual speed of the aircraft relative to the surrounding air, as it is written, relative to the surrounding air. Now, this is the real speed. Okay, this is how fast the aircraft is actually moving through the air mass. Okay, now in the formula, it is represented as V, denoted as V, and true air speed changes with altitude, and temperature. Okay, with altitude and temperature. Okay, now as you go higher, for the same indicated speed, the true airspeed will increase, because the air will get thinner and you have to move faster to create the same pressure. I hope you get it. Okay, so remember this: true airspeed is the actual speed of the aircraft relative to the surrounding air. It is denoted by V, and the changes with altitude and temperature. Okay. Then comes the EAS, which is equivalent airspeed. Got it? So we'll talk about EAS now. So now EAS is also a very important concept, and many students are very confused here. Now, equivalent airspeed is that speed which is corresponding to the dynamic pressure which is experienced by the aircraft. Now, in simple words, if I tell you, equivalent airspeed tells you how much pressure the aircraft is feeling. That is it. Okay. Now, if there were no errors at all in that system, no instrument error, no pressure error, no compressibility error, no density error, then the airspeed indicator would actually show the equivalent airspeed. Okay, that is what it is fundamentally designed to indicate. Got it? Now, if you ask, wait, speed corresponding to the dynamic pressure experienced, and this is the airspeed the ASI is fundamentally designed to indicate. And if there were no errors, the ASI would indicate the EAS. Okay, so now we'll see why the EAS is important. Okay, why is it so important? So basically, because the aircraft does not care about the true airspeed when it comes to the air performance limits. The lift depends on the dynamic pressure. Okay, drag depends on the dynamic pressure, stall speed, everything, and structural loads also depend on the dynamic pressure. If everything, maneuvering limit also, everything is depending upon the dynamic pressure. Now, dynamic pressure depends upon the equivalent airspeed. Okay, it depends on the equivalent airspeed. So the aircraft handling, how it feels on the controls when it stalls, when it reaches the structural limits, and all of that, that depends on the equivalent airspeed only, not the true airspeed. Now that is why we say that EAS is often operationally useful that than the TAS. So now we'll mark this. Lift, drag, stall speed, maneuvering limits. Everything depends on the dynamic pressure. Aircraft handling depends mainly on EAS, not TAS. And hence the EAS is often more operationally useful than the TAS. Okay. Now we'll start with the errors and corrections in the airspeed indication. Got it? So in reality, the ASI is affected by several errors. Okay. Now in a perfect world, the ASI would show the ES directly. It will show the ES directly. But we do not live in a perfect world. Okay, we are not living in a perfect world. Now, in the reality, the ASP indicator is affected by several errors. And this is where the exams love to trap the student. Got it? Now, the first error we'll start with is the instrument error. Okay, now instrument error is caused by the imperfections in the design or the manufacturing of the instrument. That is it. Okay, no instrument is 100% perfect. We know no instrument is 100% perfect. However, in the modern aircraft, the instrument error is usually very small. It is actually determined during the testing, and it is also included in the calibrated airspeed correction chart. If you have seen calibrated airspeed correction chart, and in DGC exam problems, unless they are specifically mentioning that instrument error, you can usually neglect it. So remember this. It is caused by the imperfections in the instrument design or the manufacturer, usually very small in modern aircrafts. If present, it is determined using testing and included in the calibrated airspeed correction chart. So CAS CC. Okay. Now often it is neglected in the exam problems unless it is specified. Got it? So now we'll move on to the uh, position error, also known as the pressure error. Position or pressure error, both are same. Now this is very important. The position error occurs because the pressure sensed by the pitot and the static is not exactly same as the free stream pressure. Okay, now first let us talk about the static pressure error. We'll talk about this first. Now static ports are placed on the aircraft fuselage. Suppose this is the aircraft's body. Okay, now here is the static port placed on the fuselage. Air is coming like this in this direction, and the port is here, so it is perpendicular to the airflow, and the pitot tube is placed on the wings, so it is parallel to the airflow. Got it? Now the airflow which is around the fuselage is not always smooth. Okay, it gets disturbed because of the aircraft shape, flaps or landing gear extension, or any ground effect. Okay, when the aircraft is flying close to the ground, it comes into the comes to it when it is flying close to the runway. Okay, it comes into the ground effect, which may result in the changing of the static pressure. So the result is measured static pressure is local and it is not free stream. Okay, now because of this disturbance, the static pressure at the static port is not the true ambient pressure of the free air. Okay, it is the local pressure which is disturbed. Now, when the ASI is using this incorrect static pressure, what will happen? The airspeed indication will become very inaccurate. Inaccurate. I hope you guys get it. So it will get inaccurate. Now, let us talk about the pitot pressure error. So, pitot pressure error is the pitot tube is supposed to face the airflow directly. But in the real flight, especially at high angles of attack, now angle of attack is basically, suppose this is your ground and aircraft is, suppose this is your ground, aircraft is flying like this. Okay. Now this is normal flying. Okay. And what happens when the aircraft has to climb? It increases the pitch. So this is your high angle of attack. Okay. The angle between the chord line and the relative airflow, which we'll cover in the next chapter. So remember, at high angles of attack or at low air speeds, the airflow does not hit the pitot tube straight. It does not hit straight. Suppose this is the pitot tube, the air does not hit straight. Okay, it might bend. So it will cause the pitot tube to sense less total pressure than it should. Now, when total pressure is under recorded, the airspeed shown will be obviously less than the actual. Now, the position error is tricky because it is not constant. Okay, it is changing with the angle of attack, it changes with the aircraft speed, it also changes with the aircraft's configuration. Now this is why the correction charts are provided, so remember this also. Okay, so first is this occurs due to incorrect pressure sensing. Now two pressure errors. First is static pressure error. So static ports may be located where the airflow is disturbed. And why is it disturbed? Due to the aircraft shape, due to the flaps or landing gear extension. Then why? Due to the ground effect also. So the measured static pressure is local and it is not free stream. Okay. Now comes the pitot pressure error. Now the pitot tube may not face the airflow directly, especially significant at high angles of attack, lower speeds, and it leads to under recording of the total pressure, which will obviously show the airspeed less. Now the position error basically varies with what? The angle of attack, the aircraft speed, and the configuration. So remember these three terms, AAC. Now we move to the third error, which is called the compressibility error. Okay, now this becomes important at high speeds. Okay, at low speeds we assume that the air is incompressible. We assume that the air is incompressible, but at high speeds the air starts to compress. It compresses. Okay, and when air compresses, the dynamic pressure becomes greater. What is predicted by the simple half rho v square? Okay, square formula. Okay, now why, what happens because of this? The ASI will start to overheat. It will show a higher speed than what is corresponding to the actual dynamic pressure. Now this error increases with the Mach number. Okay, the faster you go, the worse the error will become. Your speed increases, the error also increases. Okay, now compressibility correction is obtained by calculation, and it is especially important for high speed aircraft. High speed aircrafts are like the Concorde or the very high speed jets or the fighter aircrafts also. Now because of so we'll complete this first and then move forward. So at high speeds the air becomes compressible, dynamic pressure becomes greater than this, and the result is that the ASI will overheat, the error increases with the Mach number, and the correction is obtained by calculation. Got it? Now, because all of these errors, the speed that you actually see on the airspeed indicator is not equivalent to the is that speed is not the equivalent airspeed. Okay, it is something more raw, more corrected, and this speed is called the indicated airspeed or IAS. Got it? Now indicated airspeed is simply the raw reading. Remember this, it is the raw ASI reading. Okay, now nothing is corrected, no errors removed. When you correct the IAS for instrument position and the compressibility error, then only you will obtain the ES. Okay, then only finally you will obtain the ES. Now this relationship is extremely important for your exam, that IAS is what the needle shows, EAS is what the aircraft actually feels in terms of the aerodynamic forces. Okay, so remember this, because of all these errors, the speed shown on the SI is not EAS, it is called indicated airspeed, and the relationship is basically the IAS is showing the raw ASI reading, and after correcting the instrument error, the position error, and the compressibility error, then only we'll get the equivalent airspeed. Got it? So now we'll talk about the V speeds, because this is also where students often mix up everything. At low speeds, we use V speeds like stall speed, or decision speed, or rotating speed, takeoff safety speed, minimum drag speed, minimum control speed, minimum single engine best rate climb speed, and so on. Okay. Now, all these low V speeds are actually CAS. Okay, so they are calibrated airspeeds. Got it? Now they are uh, used at low speeds where the compressibility errors are very less. They are negligible actually. Okay. Now in the flight manual, they're supplied to the pilots as indicated airspeed, because that is what the pilots see. But the corrections are already applied. Okay. That means the pilot can directly fly those speeds by looking at the SI only. Got it? Now let us talk about the VMO. So remember this first. Low speeds are like stall speed, decision speed, rotating speed, then comes your takeoff safety speed, then this is your minimum drag speed, then VMC, which is minimum control speed, and VYSE, which is your single engine best rate of climb speed. Okay, now these all are your calibrated speeds, and they are used at low speeds and supplied to the pilots in the flight manual, or AFM, in as IAS. Okay, correct, and the corrections are already applied. Now let's finally talk about the VMO. Now, the maximum operating speed is known as the VMO. It is the abbreviation of the maximum operating speed. Now, always remember, if you are, suppose we are talking about VS, so we'll only see this term. S means stall. So stall, and V means speed. V is equal to speed. So stall speed. Suppose we have uh, VMO. Now, what will this mean? Minimum, maximum operating speed, maximum operating speed. So you can remember it like that. So V stands for speed, MO is the uh, abbreviated word. Okay. Now, basically, VMO is the fundamentally an EAS only. It is an EAS, and why? Because it is a high speed limitation. As we can see, it is a maximum operating speed. So it is fundamentally EAS. Okay. Now the structural limits are depending on dynamic pressure, and dynamic pressure is depending upon the EAS. So, however, even though VMO is fundamentally EAS, it is still displayed and supplied to the pilot as IAS only in the flight manual. Okay, because the pilots are flying using the ASI. So remember this also. VMO is fundamentally an EAS, but it is still displayed as IAS in the flight manual because it is a high speed limitation. Got it? So if I want to conclude this topic in your mind, always remember this logic, that the airspeed indicator measures the pressure and not the speed. Okay, and it is calibrated for the sea level density. The raw reading is the IS, and after correcting errors we get ES, and the aircraft cares about the ES because that is only representing the aerodynamic force which is acting on it. So this actually completes our chapter. We have completed all the four parts of the video, and now we are going to move to the MCQs. So I think I should do a small recap if we can. We'll complete it in 5 minutes. So first we did introduction to the atmosphere, key concept of density decreases, and the mass flowing over the aircraft also decreases. Then we saw the physical properties of the air as mass, air as a fluid, then the effect of altitude on the air properties. Then we saw what is static pressure, the units we saw, we understood what is static pressure. Then the pressure also, how many pressure units are used in aviation, then we saw that. Then the standard sea level pressure we saw, temperature units, temperature variation with altitude. Then we saw what is density, and the factors which are affecting the density. This is important. Then the pressure density and temperature relationship, density change with altitude. Then we saw ISA international standard atmosphere. Then the ICAO standard atmosphere, then the temperature lapse rate in ISA. Then we saw what is dynamic pressure. This is also important. We saw why is it existing, what are the factors affecting it, what is the total pressure, stagnation pressure, what's the formula of it, how a worked example is doing. Then effect of the speed increase, forces produced by by the dynamic pressure. Then what's the importance of aerodynamics. Then we saw the total pressure again, why dynamic pressure is critical, factors affecting density, effect of altitude. Then we saw the measuring of dynamic pressure, pitot-static principle, removing the static pressure, how is it working, airspeed indicator, how does it work. Okay, relationship between the airspeeds, then we saw, and TAS we saw. Then effect of altitude on TAS, speed of sound and Mach number we saw, critical Mach number we saw now, and today we saw what is airspeed indicator basic, calibration of the airspeed indicator, TAS, ES, why is ES important, and errors and correction in airspeed indication, three errors, and then the indicated airspeed, and which is the raw ASI reading. Then we saw the V speed. So these were the V speeds. I hope you guys remember these words: decision speed, oh sorry, stall speed, decision speed, rotating speed, minimum drag speed, minimum control speed, minimum single engine rate of climb speed. So all this is important. So we have completed the chapter now, and now we'll move to the MCQs. This was a very lengthy chapter. It was around 4 parts. So the questions are also more to keep you in good practice. So here are 14 questions. All questions are very important and they are too easy. If you have watched the videos completely, you will be able to get each and every answer. And even if you're not getting it, don't get demoralized. You guys can ask the doubt in our comment sections, and you will be given you the right guidance. Whenever you are done with these MCQs, you guys can text me on my Instagram or comment down on my post, and I'll send the answers to it. So there are 100 questions, and that is it for this chapter. So now we have completed the principles of flight atmosphere chapter. Okay, and in the next chapter we'll begin with the principle of continuity and Bernoulli's theorem and streamlines and stream tubes. So that is it for today, and I hope you guys enjoyed it. Take care, guys. Thank you. Study hard.